Welcome to Power Machines N6. This is the first of a series of videos that I am going to make to help students understand how to go about solving the type of problems that you get in your exams. So for today, we're gonna begin with STEAMPLANTs. First of all, I need to show you that this yellow circle that you see on the screen is my pointer. So whenever I am explaining, I am going to move my mouse around and you will see this yellow circle on the screen, and that will be the pointer. So you need to follow that because that shows you what exactly I am referring to on the screen. And so we're going to speak on STEAMPLANTs. And so first of all, before I get into it, I need to say that I am going to assume that you already have the basic understanding from Power N5. Okay, I am not going to go back into the fundamentals, but I am going to assume that you already have some bricks that have been laid from Power N5, and so I am just going to come and build upon that. Okay, so we're not gonna go back and explain the first principles and explain everything from scratch. I am going to assume that you already have the basic knowledge from Power Machines N5. All right, and the second thing I am going to say is that as far as the theory is concerned, I am only going to touch on the theory that you need for you to be able to solve problems. I am not gonna go deep into theory, but I am only going to touch on the minimum necessary for you to be able to solve problems. And I'm sure that's what students want. They do not want to spend too much time reading things that they don't really need. What they want is to go straight into what is really useful for them to be able to solve problems. And so this is what I am going to be doing throughout this video, and also on all the videos that I am going to record. And so today we're talking about STEAMPLANTs. And so the first thing that you need to understand when we're dealing with STEAMPLANTs is that you have two flows, okay? The first flow that you have is that of water, okay? And the water is flowing through different components of the steam plant, and then later on we will see that you also have the flow of the flue gas, which is also flowing through the various components of the steam plant. But for now, let us look at the flow of water. So when you have a steam plant, I always like to simplify the whole drawing of the steam plant like this when we're looking at the flow of water. So the first component that is really important for you to know is what we call the economizer. The second component is the evaporator, and then after the evaporator you have the superheater. And the direction of the flow of water is shown by those arrows that you see there. So the water is going from one into the economizer, and out of the economizer there you have state number 2, and then into the evaporator, and out of the evaporator you have state number 3, and then into the superheater, and out of the superheater then you have state number 4. Okay, so this is a very simplified drawing of a steam plant, but it really helps you to understand how to solve a problem, especially when the data that you have in the question are given in terms of the flow of the water. Okay, so the water goes into the economizer at state 1, and the water that goes into the economizer, we refer to that as feed water. Okay, it's called feed water, the water getting into the economizer, and that water is already at a certain temperature, and because the water is at a certain temperature, it will have heat contained in it. Okay, and so we refer to that heat as enthalpy, and in this particular case we will be speaking of specific enthalpies described with small h. Okay, and so because we are at state 1, the enthalpy of the feed water at state 1 is H1. Okay, and because the water at state 1 is in a liquid form, okay, it's in the state that is liquid, so therefore the enthalpy that you have is liquid enthalpy. Okay, and so that is HF. Okay, liquid enthalpy. Very important. also referred to as sensible heat, okay? It's all the same thing. And so H1 is an HF, okay? H1 is a liquid enthalpy or sensible heat, okay? Because the feed water going into the economizer is already at a certain temperature. It's not at 0 degrees, all right? And then after the economizer, the water goes into the economizer, and then out of the economizer, what you have, it's still water, okay? But now it is at a higher temperature, because the purpose of the economizer is to raise the temperature of the feed water, but it does not change the state of the feed water. So the water that comes out of the economizer, it's still in a liquid form, but it is at a higher temperature. And therefore, because it's still water, the enthalpy that you have after the economizer is still liquid enthalpy. It's still an HF, okay? However, it is an HF at a higher temperature. The temperature at 2 is greater than the temperature at 1, but the state of the water is still liquid, only that it is liquid water but at a higher temperature. And then that water goes into the evaporator, and the purpose of the evaporator is to turn the water into steam, okay? That is why we even call it an evaporator. It's because it evaporates the water. It turns the water into steam. And so out of the evaporator, what you will have is steam, okay? But that steam is usually going to be wet, okay? Wet steam. And we know from power N5, if the steam is wet, therefore the enthalpy that you have at state 3 will be a wet enthalpy. And wet enthalpy, HW, is equal to liquid enthalpy plus the dryness fraction multiplied by the enthalpy of evaporation, which is HFG. Okay, really important. So out of the evaporator, what you have is steam, which is usually wet. And the enthalpy out of the evaporator, we refer to it as H3, okay, because that is state 3, okay. So you have hot water in a liquid form getting into the evaporator, and out of the evaporator what you have is steam, which is usually wet steam, okay. So it's an HW, and then that wet steam gets into the superheater, and the purpose of the superheater is to superheat the steam. So naturally at state 4, out of the superheater, what you're going to have is superheated steam, okay. And the formula for superheated steam is given to you by the formula for HSAP, okay. So H4, the enthalpy at state 4 is superheated enthalpy, okay, and so it is HSUP. Some people refer to it as HSUP, but I like to say HSAP, okay. So H4 is an HSAP. Now what we know with the enthalpy of superheated steam is that if in your question, in your exam, you are given a value for Cp, okay, therefore the formula for HSAP is equal to Hg plus Cp multiplied by Tsap minus Ts, and Ts of course is the saturation temperature that you read from your steam tables, okay. Really important. But sometimes you can have a question where the Cp value is not given, and then what you do, you just read HSAP from your steam tables. So you're gonna use your tables for you to read HSAP if the Cp value for superheated steam is not given. Really, really important. Another thing that I need to say is that the pressure is the same, okay. The pressure is the same between state 3 and state 4. The pressure remains constant, okay. The pressure remains constant. So the pressure that you have outside of the evaporator and into the superheater is the same pressure that you will have outside of the superheater. So throughout the process, the pressure remains the same. So usually in a question that is given to you on steam plants, you will see a certain pressure that is given to you. That pressure is what you will use when you are doing your calculation for H3, which is usually an H wet, okay, wet enthalpy, and it's the same pressure that you will also use in getting your readings to find HSUP, HSAP, okay, because the pressure is the same before the superheater and after the superheater. Really important to remember that, okay. That is why you saw on top here I wrote P3 is equal to P4. The pressure is the same, okay? The pressure is the same. And then now, when you have water flowing like that, when you have a question where you're looking at the flow of water, in order for you to find the heat to the economizer, the heat that has been absorbed by the economizer, what the equation that you need to use is this one. Okay, Q echo is equal to ms over mf multiplied by H2 minus H1. Okay, ms is the mass of steam consumed per hour or per second, depending on what you have in that question, and mf is the mass of fuel or the mass of coal also burnt per hour. Okay, so that's what you have, and then you multiply that by the change in enthalpy. Okay, so the enthalpy after the economizer, which is H2, minus the enthalpy of the feed water getting into the economizer, which is H1. And when you use that equation, you can then find the heat that has been absorbed by the economizer. Really important. And then we have a similar equation for the heat absorbed by the evaporator, but notice that this time that the enthalpy difference is between H3 and H2, okay, because because the water flows into the evaporator with an enthalpy of H2 and then comes out of the evaporator with an enthalpy of H3, and therefore the heat absorbed by the evaporator will be ms over mf multiplied by H3 minus H2. Okay, and then you also have an equation for heat absorbed by the superheater. It's again very similar to the previous two equations that I showed you. However, in this case now you have H4 minus H3, because if you look at the superheater, the enthalpy of the wet steam that goes into the superheater is H3, and then the enthalpy of the superheated steam that comes out of the superheater is H4. Okay, so therefore to find the heat that has been absorbed by the superheater, you then use that equation Q SAP is equal to ms over mf multiplied by H4 minus H3. Really important. So it's really important to understand that when you have a question on steam plants, sometimes you can have a question where what you're looking at is the flow of water, and in other times you could get a question where what you're looking at is the flow of flue gas, which we are about to look at very soon. And in some questions it's some sort of a combination of the two. But for you to be able to solve questions on steam plants, what you need is to understand how the water is flowing and also how the flue gas is flowing. So the water flows from the economizer into the evaporator and into the superheater. Okay, that is the direction of the flow of water. So you need to understand that very well and to remember that always. But then you also have the flow of flue gas. So how does the flue gas flow? This is how the flue gas flows. Okay, and so first it's important for me to explain to you what is flue gas. Many people do not know what is meant by flue gas, but basically flue gas is what you have when you have fuel that has gone through combustion with air and that has been burnt, and then you have that gas that is coming out of that. That's what we refer to as flue gas. Okay, really important. And the direction of flow of flue gas is what you see depicted in this picture. Really important. So first of all, you will have air. Okay, air will come in contact with the fuel, and the air and the fuel will mix together and combustion is going to take place. And after air has mixed with fuel, what you have now is flue gas. Okay, this is what you see here, flue gas. So you have air coming in contact with the fuel, and then combustion takes place, and then what you have now is flue gas. So it's easy to understand that this flue gas that you see here is going to be a mixture of fuel and of air. Okay, and so if it is a mixture of fuel and of air, therefore if you want to know the amount of flue gas that you have, you need to sum up the amount of fuel that you have with the amount of air that you have. And I will give you an example. In some of the questions that you may have, they may say to you, for example, that the air fuel ratio is given as 18 kilograms of air per kilogram of fuel. That means in order to burn 1 kilogram of fuel, you need 18 kilograms of air. Okay, but because air and fuel are burnt together, therefore the flue gas that you have is a combination or a sum of the air and of the fuel. And that is why the mass of flue gas is always equal to the mass of air plus 1 when that is given to you as an air to fuel ratio. Okay, like in this particular example that I have at the bottom of the screen, you are given 18 kilograms of air per kilogram of fuel. So the air to fuel ratio is 18:1, what you see here in brackets. Okay, and therefore if you want to know the mass of flue gas, that will be equal to the mass of the air plus the mass of the fuel. In this case, for 18 kilograms of air, you have 1 kilogram of fuel. So the mass of the air is 18 plus the 1 kilogram of fuel. Therefore, the mass of the flue gas that you're going to deal with when you have an air to fuel ratio of 18:1 is going to be 19. Okay, so always remember that the mass of flue gas is equal to the mass of air plus 1 when you are given an air fuel ratio. Really, really important. So now let us look at the flow of the flue gas. So you have the flue gas here at state 1. Okay, you have the flue gas here at position 1. Okay, as you can see. And so this flue gas, how does it go? We saw that when it's water, the water flows from the economizer into the evaporator and into the superheater, okay? But the flue gas flows from the evaporator, as you can see, into the superheater and then into the economizer. So it's really important for you to know how the flue gas is flowing, okay? In what arrangement. Really important. It's not the same arrangement as the flow of water. So it's really important for you to understand how the flue gas is flowing. And so what you see that I've written here, TFG1, that will be the temperature of the flue gas at position 1, just before it gets into the evaporator. What you see written here as TFG2 is the temperature of the flue gas out of the evaporator, okay? Just before it gets into the superheater. And what you see here, TFG3, is the temperature of the flue gas out of the superheater just before it gets into the economizer. And then you have TFG4, which is the temperature of the flue gas out of the economizer just before it gets into the air heater. And then you have TFG5, which is the temperature of the flue gas out of the air heater just before it gets into the chimney. Okay, and then out of the chimney, what you pretty much have is the atmosphere. Okay, if you've ever looked at the chimney, even on top of a house, the discharge of the chimney goes into the atmosphere. So what you have out of the chimney is just the atmosphere. So the temperature out of the chimney is atmospheric temperature. Whatever temperature you will get in your question that they will say the atmosphere is at such temperature, that is the temperature out of the chimney, okay? Sometimes they may also refer to it as the boiler room temperature. That is still the atmospheric temperature. It's the temperature that you have in the open. Sometimes in some questions they may call it atmospheric temperature. In other questions they may refer to it as boiler room temperature. It's the same thing, okay? Really, really important to know that. So please know the direction of flow of the flue gas, because it's really important to also know that, because the heat absorbed to the various components, the evaporator, the superheater, the economizer, you can also find it using equations that relate the mass of the flue gas to the change in temperature before and after each of these components. difference. What I mean by that is that if, for instance, we wanted to know what is the heat absorbed by the evaporator, if we had all the data of the flow of the flue gas, we could also use this equation. So heat absorbed by the evaporator is equal to the mass of flue gas multiplied by the specific heat capacity at constant pressure of the flue gas, Cp of the flue gas. So one mistake that I see many students do is that they sometimes use Cp of superheated steam in the equation for the flue gas. That is a terrible mistake, okay? When you are dealing with the equation where you are using the mass of the flue gas and the temperature of the flue gas to find the heat absorbed by the evaporator or the superheater or the economizer, the Cp that you need to use in that equation is that of the flue gas. Do not use that of superheated steam. So the heat absorbed by the evaporator can also be found using the equation that you see there with the mass of the flue gas multiplied by the specific heat capacity of the flue gas and multiplied by the change in temperature between the temperature of the flue gas that goes into the evaporator and the temperature of the flue gas after the evaporator, because the flue gas is very hot, okay? At state 1, the flue gas is very hot, and then it loses some of that heat when it passes through the evaporator. And then at state 2, it's still hot, but not as hot as it was at state 1. And then it goes into the superheater and loses again some of that heat, and then gets to state 3, at position 3, where it's even lower, but still hot, and then loses even some of that heat again until it gets to state 4, and so on. That is the way it is. So understand that flue gas is initially very hot, and then as it begins to travel through the different components of the steam plant, it is losing some of that heat, and it is that heat that the evaporator will absorb in order to do its work, and then the superheater will again absorb the heat that is there, and the economizer will absorb again what is left of it, in order to be able to do the work that each of these components need to do. So the flue gas is initially super hot and then begins to lose that heat as it travels through the components of the steam plant. So we have seen what is the heat absorbed by the evaporator when you look at it from the angle of the flue gas, and this is the equation for it. What you see here, okay, that's the equation for it, okay, and this will give you the same number that you will get if you had used the equation with ms over mf multiplied by h3 minus h2, okay? That will give you the same number, okay? So this is just an alternative equation to find the heat absorbed by the evaporator. And then you have another similar equation for the heat absorbed by the superheater, but just bear in mind here that the temperature difference is now between temperature of the flue gas at state 2 and temperature of the flue gas at state 3. And again, I repeat, the temperature of the flue gas at state 2 is higher than the temperature of the flue gas at state 3, because as the flue gas is traveling through the different components of the steam plants, it is giving them heat for them to be able to do the work that they need to do, okay? Really important. And finally, you also have the heat absorbed by the economizer, and again, what you see here is a similar equation, okay? Very, very important. But now, I am going to add two other equations, because in some of the questions, you do get them asking you to give them maybe the heat that has been absorbed by the air heater, and it is still a very similar equation to these three that I've just shown you, and this is what it is, okay? You will again multiply the mass of the flue gas by Cp of the flue gas, and then multiply that by a change in temperature. But again, as you can see, in this case, the air heater, the change in temperature is between the temperature of the flue gas at state 4 and then the temperature of the flue gas at state 5, okay? So that difference, that's what you look at when you try to find the heat absorbed by the air heater. And then finally, they may also ask you to find the heat absorbed by the chimney. and what you will have here will be therefore the temperature, the mass of the flue gas multiplied by Cp of the flue gas, and then multiplied by the change in temperature between the temperature of the flue gas that goes into the chimney, and of course outside of the chimney the temperature that you have is the temperature of the atmosphere, or they may also refer to it sometimes as the boiler room temperature. It's all the same thing. Okay, really important to understand that. Now, in some of the questions you may not have a chimney, for instance, but you may have an air heater. Okay, so if that's the case, then of course you will limit yourself to the heat absorbed to the air heater. Okay, you will not have an equation for the chimney. And in some other problems you may not have an air heater, okay, but after the economizer you will directly have the chimney, and so TFG4 and TFG5 will all become just one. Okay, they will all be just TFG4, okay, because you will not have a state 5. Okay, it will just be after the economizer, state 4, and then directly the chimney. Okay, really important to understand that, but the logic in applying the equations remain the same. Okay, so that's all you really need to understand as far as the theory for steam plants is concerned. At least what I've given you is enough for you to be able to tackle any kind of problems on steam plants that you may face in an exam. And so now what we're going to do is look at two different examples, and in those examples we will apply what we just talked about, so that you understand how you are supposed to go about solving these problems on steam plants. Okay, before I get to the examples, okay, I forgot that I needed to speak about efficiencies. Okay, so this is a really quick one. Okay, the formula for efficiency of a steam plant, the efficiency of a steam plant is given by that. Okay, really easy. You know what everything stands for in that equation. So that is the formula for the efficiency of a steam plant. And then there is also what we refer to as the equivalent evaporation from and at 100 degrees. And the equation for that is given by this. Okay, and so you already know what everything in that equation stands for. So these are just two equations that you really need to know before we look at the examples. So let us now get quickly into examples. And so all the examples we're going to look at are all coming from past papers. Okay, they're all coming from past papers. So there were students that wrote on these questions, and so I am just taking selected questions from past papers that I think are really interesting, and then we look at them together, and I try to explain as much as I can so that you understand as well as you can. Okay, really important to do that before the end of this video. Okay, so the first example we're going to look at, we're going to look at two examples, but the first one, it goes like this. I am going to read it and make sense of everything that you have in the question. So the question says, a boiler plant consisting of an evaporator, an economizer, and a superheater generates steam at a pressure of 1,500 kilopascals and a temperature of 350 degrees. Okay, so the steam that is generated by this steam plant comes out at a pressure of 1,500 kilopascals and a temperature of 350 degrees. So if you remember the flow of water that I showed you in the previous slide, you will remember that the steam comes out of the superheater. Okay, that is where it comes out. It comes out of the superheater. And so that steam that is out of the superheater is superheated steam. Okay, so the pressure that you have of 1,500 kilopascals is P4, and the temperature that you have of 350 degrees Celsius is TSUP. In fact, if you go on your steam tables and you check the saturation temperature for 1,500 kilopascals, you will find it to be lower than 350 degrees, which means that the state of this steam, okay, is already at a temperature that is higher than saturation temperature. Therefore, it is superheated, which makes sense because the steam that comes out of the steam plant is coming out of the superheater, and therefore it must be superheated. So we have this pressure of 1500 kilopascals. And remember what I told you, the pressure after the superheater is equal to the pressure before the superheater. Okay, so P3 is 1500 kilopascals, and this is also equal to P4. All right, and then you are told that it is coming out at a rate of 600 kilograms per hour. So this steam plant is producing 600 kilograms of steam per hour, and so that number that you see is actually MS, the mass of steam. Okay, really important. Now, at the entry to the superheater, the steam is 90% dry. The entry to the superheater is the exit of the evaporator. So the steam is coming out of the evaporator and into the superheater. So when they say at the entry to the superheater, what they also mean is at the exit of the evaporator. Okay, really important. So we know that at the exit of the evaporator, its name itself means to evaporate. Okay, so the evaporator evaporates, so it turns the water into steam, and you are told that the dryness fraction of the steam is actually 0.9. That is what is meant by the steam is 90% dry. Okay, it means it's wet steam, but its dryness fraction is 0.9. Okay, really important. And then you are told that the temperature of the feed water that is entering the economizer is 47.7 degrees. And remember, the water is liquid. Therefore, if it is entering at 47.7 degrees, the enthalpy in that water will be the liquid enthalpy that you read from the steam tables, HF, at 47.7 degrees. And you are told that that water leaves the economizer at a temperature of 98.2 degrees. Okay, and so the water leaving the economizer is the water that is about to get into the evaporator. But remember, after the economizer, I told you that you still have water, but that water is now at a higher temperature. That is why you see here the temperature of the water after the economizer is 98.2 degrees, which is greater of the temperature of the feed water that went into the economizer at 47.7 degrees. Okay, really important. And then you are given the calorific value of the coal. You are told coal with a calorific value of 35,000 kilojoules per kg. So this is CV. Calorific value of the coal is 35,000. Okay, and it is being burned at a rate of 620 kilograms per hour. So now this 620 kilograms per hour is the mass of the coal, or the mass of the fuel, MF or MC. Okay, and then you are told that air is also being supplied to the burner at a rate of 60 kilograms of air per kilogram of coal. Okay, so this is the air to fuel ratio. It's 16 kg of air per kg of coal. So the air to fuel ratio is 16:1. Okay, really important. And you are given the atmospheric temperature as 25 degrees. Okay, the atmospheric temperature is 25 degrees. And then the temperature of the flue gas when it leaves the economizer. Remember the flow of the flue gas. When you leave the economizer, when the flue gas leaves the economizer, it's just about to get into the air heater. But if you do not have an air heater, then it's about to get into the chimney. Okay, so you are told that the temperature of the flue gas when it leaves the economizer is 220 degrees. And you are told to take the specific heat capacity of the flue gas as 1.045 kilojoules per kg Kelvin. And notice in this whole question, we are not told that we have an air heater, and therefore you can conclude that the flue gas flows directly out of the economizer into the chimney. Okay, if you do not remember that diagram, you can pause the video and go back. Okay, you can rewind, go back and look at the diagram of the flow of the flue gas, and you will see that directly after the economizer is the air heater. But if you do not have an air heater, therefore the flue gas will go directly into the chimney. Okay, and you are told that the temperature of the flue gas when it leaves the economizer, just about to get into the chimney, is 220 degrees. Okay, very, very important. And then they gave you the specific heat capacity of the flue gas as 1.045 kilojoules per kg Kelvin. Okay, so now this specific heat capacity is for the flue gas. You cannot possibly use that when you are trying to find equations maybe for steam. Okay, the specific heat capacity for the flue gas cannot be used for steam, and the specific heat capacity for the steam cannot be used for the flue gas. Okay, and then now they want you to find the efficiency of the plant, the equivalent evaporation from and at 100 degrees, and then they want to find the heat that has been absorbed by the economizer, the evaporator, the superheater, and the chimney, and finally they want you to draw an energy balance sheet. Okay, and including the heat that is lost to radiation. Okay, that is just the heat that remains or the heat that is not accounted for. Okay, that is what is meant by the heat that is lost to radiation. So let us get into it. Okay, let us get into it. So first, what we need to find is the efficiency. Okay, question 1a, find the efficiency. And so the equation for the efficiency is this one. We saw that earlier. And as you can see in this specific question, okay, we can easily find H4, for instance, and H1. They are all easy to find. So let's look at that. First, H1 is equal to HF at 47.7 degrees. So you go on your steam tables and you look for the HF value at 47.7 degrees. Why is it that we're looking at HF? Because it's liquid enthalpy. The water, H1 is the enthalpy of the water getting into the economizer. And the water into the economizer is still liquid. Okay, and so the enthalpy that is contained in that water is an HF value, because HF is liquid enthalpy, or also referred to as sensible heat. Okay, and so if you read HF at 47.7 degrees, it's 200 kilojoules per kg. Okay, H4, we will also find it. In this particular question, you will see that we are not given a CP value for superheated steam. And I said earlier, if you are looking for H4, which is an HSAP, and you are not given a CP value for superheated steam, then you do not have a choice but to read it directly from the steam tables. And so to find HSAP, what we did, we read the HSAP value in the superheated steam tables at a pressure of 1,500 kilopascals and a temperature of 350 degrees. And when you read that value, what you have is 3,148 kilojoules per kg. So now we have H1, we have H4, MS, MF, and CV are given in the question, so you can then go directly and find the efficiency of this particular steam plant. And what you get is 81.5%. Okay, 81.5%. Really important. And then point number B, what they want you to find is the equivalent evaporation from and at 100 degrees. In one of my face-to-face classes, one of the students was trying to use this 100 degrees to try and find enthalpy values, okay? Because it says the equivalent evaporation from and at 100 degrees. So they went to the steam tables and they tried to use this 100 degrees to read H values. But that will be a terrible and stupid mistake, okay? Because when we say the equivalent evaporation from and at 100 degrees, this is how it is called, okay? That's the name of it, okay? Do not think that this 100 degrees that is given to you is data for you to solve the problem. No, this is not data for you to solve the problem. This is how we call this particular number that we're trying to get. It's called the equivalent evaporation from and at 100 degrees. Okay, really, really important. So don't try to use this 100 degrees in your steam tables to try and find H values. That will be a stupid and terrible mistake. Okay, so to find the equivalent evaporation, this is the equation, and we already found H1 and H4, so we can just plug in the numbers and we get 12.6 kilograms of steam per kilogram of coal. Okay, really, really important. Just plugging in the numbers. All right. So now, point number C is to find the heat to the economizer, the evaporator, the superheater, and the chimney in kilojoules per kg. Okay, so let's go ahead and do that. So point number C. First, we have to find the heat to the economizer. And this is the equation for heat to the economizer. We already found H1 in the previous slide. Now, what is H2? To find H2, remember I told you H2 is the enthalpy of the water out of the economizer. And out of the economizer, you still have water in liquid form, but it is at a higher temperature, hotter water, okay? It's hotter than the water into the economizer because the economizer raises the temperature of the water. So to find H2, we just read the HF value directly from the table, but at a higher temperature, okay? This is the H1 that we had already found, and now H2 is the HF value at a higher temperature of 98.2 degrees, and that will give you 412 kilojoules per kilogram. And this is read directly from the table. HF at 98.2 degrees. And once you have that, you can directly now find the heat to the economizer like that. Really easy, really straightforward. And now finding the heat to the evaporator, which is the second one, we will use again the equation for the heat to the evaporator. But in this case now, we do have H2, but we need to find H3. And H3 is the enthalpy of the wet steam out of the evaporator, okay? If you do not remember the flow of water, you can go back, okay, and look at that diagram that I gave you of the flow of water, and you will see that H3 is the enthalpy of wet steam out of the evaporator, okay? The steam that comes out of the evaporator has an enthalpy that is H3, and it is wet steam, okay? And so we will find it like that. H3 is an H wet, and it's equal to HF plus XHFG, okay? But in this case, what pressure are we going to use? We're going to use the pressure at the exit of the superheater. Remember I told you pressure before the superheater is equal to pressure outside of the superheater. The pressure remains constant like that in the steam plant, okay? And so you're just going to use that pressure of 1,500 kilopascals, and you will read the HF value at that pressure and also the HFG value at that pressure, okay? And in this question, you've been given the dryness fraction at the entry of the superheater, or which is also the exit of the evaporator, okay? You've been given the dryness fraction there, so you just plug in the numbers using that equation, and that gives you the value for H3. And once you get the value for H3, you can then plug that into the equation for the heat absorbed by the evaporator, and you will get the answer for the heat that has been absorbed by the evaporator here, 21,130.6 kilojoules per kg, okay? Really straightforward, really easy to do if you understand the two diagrams that I gave you for the flow of water and for the flow of the flue gas, okay? Those are really important for you to understand to be able to solve any steam plant problem. Now, let us look at the heat absorbed by the superheater, okay? And this is the equation. Now, in the previous slide, we found H3. So now we need to find H4, but remember we already found H4 when we were looking for the efficiency. So you just go ahead and you plug in the numbers, okay? And that is what you get for Q sup, okay, the heat absorbed by the superheater. And now we need to find the heat absorbed by the chimney. Now, for you to be able to find the heat absorbed by the chimney, okay, you have to remember that water does not flow into the chimney. But what flows into the chimney is flue gas. So you now need to remember that flow of the flue gas, how the flue gas flows. Remember that diagram. If you can't remember it, you are welcome to rewind the video and look at that diagram, okay? But you will see that the flue gas flows out of the economizer into the chimney, and then out of the chimney into the atmosphere. So to find the heat that has been absorbed by the chimney, the equation that you're going to use is this one, okay? TFG5 minus T of the atmosphere. That is what we're going to look at here. Okay, so the heat absorbed by the chimney is equal to the mass of the flue gas multiplied by the specific heat capacity of the flue gas multiplied by the temperature of the flue gas at location 5, at state 5, minus the temperature of the atmosphere, the atmospheric temperature. Now, in this particular question, we do not have an air heater, okay? And because we don't have that, therefore TFG5 is the same as TFG4, okay? So you will just take the temperature of the flue gas out of the economizer minus the temperature of the atmosphere, or the atmospheric temperature, okay? And so if you do that, you already have everything that you need. Remember, the air-fuel ratio is 16:1. It's given in the question, 16 kilograms of air per kilogram of coal. So the air-to-fuel ratio is 16:1. Therefore, the mass of the flue gas will be 16 plus 1, as you see here, multiplied by the specific heat capacity of the flue gas, okay, and then multiplied by the temperature out of the economizer, which is given in the question somewhere here, okay. The flue gas, when it leaves the economizer, is 220 degrees, so that is what you're going to take here, minus the atmospheric temperature, which is 25, and that will give you the heat that has been absorbed by the chimney, as you see here. Really, really important. And then after that, now the last part of the question, which is question D, is to draw a heat balance sheet. And what they mean by that is a table that looks like this, okay? So on the far left of the table, okay, what you have there is the total heat that the fuel is providing in kilojoules per kg. In other words, that is the calorific value of the fuel. That is what you have on the left side of the table, 35,000, okay? And then this bottom row that you see here, this is where we put all the totals. We put the totals in this bottom row here. But let us look first at what you have here. On the left of this table, what you have here is the calorific value of the fuel. So whenever you are told to draw a balance sheet, a heat balance sheet, okay, just make a table like that, and on the left of the table you will have the calorific value of the fuel, okay, and then in the middle of the table you will have the heat that has been absorbed by the different components in these particular questions. In the question that you have, okay, in this particular question, what we had was the economizer, we had the evaporator, the superheater. We did not have the air heater, but we did have a chimney, okay. So you just write all the heat that the heat values that you have for each of the components, and then at the bottom of this middle column of the table, just before the total, at the bottom here you write the remaining, okay. So you will take the total calorific value of the fuel minus the sum of all of these heat absorbed by the different components of these steam plants. Okay, and that will give you the heat that remains, okay. And this is what in this question was referred to as the heat lost to radiation, okay. Really, really important. And then if you sum all these heat values absorbed by each of these components, you will again get 35,000 here at the bottom, okay. And then now you need to say what percentage each of the components of the steam plant absorbed in terms of heat. And the way you do that, you will take the heat absorbed by the specific component, you divide that by the total heat available in the fuel, and you multiply that by 100, and that will give you the percentage of heat that has been absorbed by that specific component. So let us look, for instance, at the case of the superheater here. The heat absorbed by the superheater was 5,346.8, okay. So I take that, I divide by the calorific value of the fuel, which is the total heat available per kg of steam I mean, the total heat available in kilojoules per kg of fuel, okay, 35,000. So you take the heat absorbed by the superheater, you divide by the 35,000, and you multiply that by 100, and therefore we can see that the portion of heat absorbed by the superheater is actually 15.23%. So you do that for all the components of this particular steam plant, and you also do that for also the remaining, okay, the heat that is not accounted for, or the heat lost to radiation, and you also find what percentage that constitutes, okay. And then when you sum them up, they should give you 100%, okay. Really, really important. And so when you do that, you've pretty much done everything that was required from you in this question, okay. And so let us now go into another example. In the last 10 minutes that we have, let us look at another example, and let's see how we're gonna go about doing that. So this is the question that we have, okay. Again, you have a steam plant which is consisting of an economizer, an evaporator, and a superheater, and you are told that the steam plant is generating 9.5 kilograms of steam per kilogram of fuel. Now, this is very important here because you are given the mass of steam not in kilograms per hour, but you are given the mass of steam in kilograms of steam per kilogram of fuel. In other words, what you see there, 9.5, is actually ms divided by mf. Okay, so everywhere in your equations where you have ms divided by mf, you will just replace that ratio by 9.5, because the mass that you have here is a mass of steam not given in kilograms per hour, but rather in kilograms of steam per kilograms of fuel. Okay, so therefore ms by mf will be 9.5. Okay, and you are also given the pressure in the steam plant, which is 2 megapascals. And then in this table, they gave you all the data that has been recorded when you're dealing with this steam plant. Okay, and so you have the calorific value of the fuel, which is 31 megajoules per kg. And remember, in our equations, we're working with kilojoules. So you need to change that 31 megajoules to kilojoules per kg. Okay, so that will give you 31,000 kilojoules per kg. That's the calorific value of this fuel. You are given the thermal efficiency of the plant, which is 82%. Okay, we already saw the equation for efficiency. So that efficiency is 82% in this problem. Now you are given the temperature of the flue gas at the chimney base. Okay, so now you can again rewind the video and go back to that diagram that I gave you of the flow of the flue gas, and you will see that at the chimney base you are out of the air heater. Okay, out of the air heater into the chimney. So that's where the chimney base is. It's at the exit of the air heater. If you do not have an air heater, therefore the chimney base will be the exit of the economizer. Okay, the exit of the economizer will be the chimney base. Very important to remember. The air-fuel ratio is given to you as 18:1. Okay. Immediately from that, you understand that the mass of the flue gas will be 18 plus 1. Okay. So the air-fuel ratio is 18:1. Therefore, mass of the flue gas is 18 plus 1. And you are also given the specific heat capacity of the superheated steam, 2.6 kilojoules per kg Kelvin. Now, this is the specific heat capacity of the superheated steam. So do not use this CP value when you are using equations for the flue gas. When you're using equations for the flue gas, use the specific heat capacity of the flue gas. Really important. Okay? The CP for superheated steam, you only use it with superheated steam. Really, really important. Now, you are also given the temperature of the feed water entering the evaporator. Okay, so that's out of the economizer into the evaporator, because when they speak of the feed water, now you are no longer looking at the diagram for the flow of the flue gas, but now you are in the diagram for the flow of water. Okay, and you are told that the temperature of the feed water entering the evaporator is 101.7 degrees. Okay, so the feed water entering the evaporator is the same as the feed water that came out of the economizer. Okay, so it's H2. Okay, you will look for H2 at this temperature here, and this H2 will be an HF value because the water out of the economizer is still in a liquid state, so it's a liquid enthalpy, HF at 101 at 107.1 degrees. Okay, and then you have the temperature of the flue gas leaving the evaporator. Okay, so do not get confused when they give you the temperature of the feed water. Okay, then you need to look at the diagram of the flow of water. When they give you the temperature of the flue gas, then you need to look at the diagram of the flue gas. Okay, in this case they gave you the temperature of the flue gas, of the flue gases, okay, leaving the evaporator. And if you think about it, the flue gases leaving the evaporator, if you look at that diagram, those flue gases are going into the superheater. Okay, so you have the temperature of the flue gases leaving the evaporator. That's the same thing as the temperature of the flue gases going into the superheater in the flue gas diagram. Okay, the flue gas flow diagram that I showed you. And then you also have the temperature of the flue gases leaving the superheater. Now, the temperature of the flue gases leaving the superheater is the same thing as the temperature of the flue gases going into the economizer. Just rewind if you need to and look at the diagram of the flow of the flue gas and you will see. And then you have the specific heat capacity of the flue gases, which is given to you as 1.05 kilojoules per kg Kelvin. Now, this CP is to be used only with the flue gases. Do not use that with steam. That will be a terrible mistake. Okay, bear that in mind. And then you are given the temperature of the boiler room. Remember, I told you earlier, when they give you the temperature of the boiler room, that's the same thing as saying atmospheric temperature is 24 degrees, okay? 24 degrees. And now what they want is the heat to the economizer, the evaporator, and the superheater. And then they want the dryness fraction of the steam entering the superheater, okay? And remember, the steam entering the superheater, we're looking at the flow of water. And if you look at the enthalpy before the superheater, it's actually a wet enthalpy. Now they want the dryness fraction for that. And then you have the temperature of the they also want the temperature of the superheated steam leaving the superheater. Okay, so you will use H sup, H4, which is equal to an H sup. And in that equation, you will try to find the T sup value, okay? The T sup value, that's what you will look for. And finally, they want the percentage of heat lost to the chimney and the percentage of heat lost and accounted for. Okay, so let us get right into that very quickly. Okay, so first we need to find the heat to the economizer. Now, in this particular question, what you will find is that you do not have enough information for you to use that formula of ms over mf multiplied by h2 minus h1 to find the heat to the economizer. However, you have enough information to using the diagram for the flow of the flue gas, okay? You have enough information using that diagram to be able to come up with the heat absorbed by the economizer. And so if you think about it, you will see that you are given in the question the temperature of the flue gas leaving the superheater, and that is 300 degrees, and that is TFG, temperature of the flue gas at state 3. Okay, it's leaving the superheater. When it leaves the superheater, it's going into the economizer. And then you also have the temperature of the flue gas that leaves, okay, the economizer. But the way they put it in the question, they said the temperature of the flue gas at the chimney base, okay? The chimney base is the same thing as the exit of the economizer. In this case, we do not have an air heater, and therefore the chimney base is the same thing as the exit of the economizer. So the flue gas come out of the economizer, it's at the chimney base about to go into the chimney. Okay, and so that temperature is given to you as 200 degrees, and you can then just go ahead and use that equation that you have there when you look at that diagram for the flow of flue gas, and you will see that you can just use it directly. If you understand that diagram, you can use it directly like this, and you come up with this number. And again, look at the mass of the flue gas. It's 18 plus 1, 18 kilograms of air and 1 kilogram of fuel burning together. 18 plus 1, that is the flue gas, and you get Q to the economizer. And then you have to find Q to the evaporator. But now you do not have enough information in the question to be able to find Q to the evaporator. Even if you look at the diagram for the flow of flue gas, you don't have enough information to find Q for the evaporator. Okay, and so what we will do, we will find Q to the superheater first, and then once we have Q to the superheater, then we will come back using the efficiency equation and find Q to the evaporator. And Q to the superheater, again, it's straightforward using that equation that you have there. You are told in the question that you have the flue gas that leaves the evaporator. That flue gas is at a temperature of 465. When it leaves the evaporator, it's getting into the superheater. And then you also have the temperature of the flue gas leaving the superheater. And so you have all the temperatures that you need to be able to use that equation. And please notice that the CP value that I am using when I use these equations for the flow of the flue gas, I am using the CP value for the flue gas, okay, which is 1.05. I'm not using the CP value for the steam. Okay, do not make that mistake. It's gonna cost you a lot. Okay, it's CP for the flue gas. In fact, here in the equation for Q to the economizer, it was supposed to say CP of the flue gas. Okay, I just forgot to correct it here. It's CP for the flue gas. Okay, bear that in mind, really important. And so once you have Q sup, the heat absorbed by the superheater, you can then go and use the efficiency equation like that, and you have all the numbers that you need. The only thing that you do not have is Q to the evaporator. Remember, in the question you are told that the thermal efficiency of the plant is 82%, so you will replace that efficiency later by 0.82, and you replace Q echo by what you have, 1995, Q sup and CV, and the only thing that will remain will be Q eva, okay, and you can find Q to the evaporator by just plugging in the numbers, and you will find it to be like that, okay, 20,133.25, okay. And once you've done that, then you have given them what they want: Q to the economizer, Q to the evaporator, and Q to the superheater. Now, what we need to find now in question B is the dryness fraction of the steam entering the superheater, okay, really important. Dryness fraction of the steam entering the superheater. And then for that we will use, now we found a value for the heat absorbed by the evaporator. Now we can use the equation when we're looking at the flow of water, okay, and Q to the evaporator is given by that equation. Now for us to be able to find the dryness fraction, we need to find H3 first, okay. H2 is actually quite easy to find because you are given the temperature of the feed water entering the evaporator, okay. The temperature of the feed water entering the evaporator, like I said earlier, that's the temperature of the feed water out of the economizer. And you just have to use that temperature and the steam tables and read the value for HF at that temperature to get H2. And if you do that, that's what you get. HF at 107.1 degrees is 449. And so plugging in all the numbers into the equation for the heat absorbed by the evaporator, we find that the only thing that we do not have is H3, okay? And remember what I said earlier, MS over MF in this case is 9.5, okay? So that's the 9.5 that you see here. And now plugging in every letter by its number, replacing every letter with its number, what we find is that the only thing that we do not know is H3. And we can then solve for H3 and find it like that. And remember Q EVA, we found it in the previous slide to be 20,133.25. So you just plug it in that, and then you solve for H3. Once you have H3, remember H3 is an H wet, and so you can just go and now look for HF at 2000 kilopascals, because that's the pressure in the steam plant, and HFG at 2000 kilopascals, okay? And H3 is an H wet, so it's this equation that you're going to use, and you plug in again all the numbers that you already have. 908 is HF at 2000 kilopascals, 1889 is HFG at 2000 kilopascals, okay? So the only thing that you do not have when you replace everything by what it stands for is X, and therefore you can just solve for X, and you will find that the dryness fraction is actually 0.88 at the entrance to the superheater or at the exit of the evaporator. It's the same location, okay? The exit of the evaporator in the flow of water is the entrance to the superheater, okay? Really, really important. So now we found the dryness fraction at the entrance to the superheater. Now let's find the temperature of the superheated steam, which is point number C, okay? And this is the equation, okay? When you look at the flow of water, okay, at the exit of the superheater, the steam is superheated, and therefore the enthalpy H4 is an H sup, the enthalpy of superheated steam, and it's given by Hg plus Cp T sup minus Ts. Okay, in this case, Hg will be at 2000 kilopascals because that's the pressure in this steam plant, and Ts will be the saturation temperature at 2000 kilopascals, okay? And so right now we do not yet have H4, okay? We do not know what H4 is. We're gonna need to find H4 first, and then we will replace H4 by what it is in this equation, and then we will have everything in the equation, and we can then solve for T sup. So let us begin by finding H4. And to find H4, you just come in the Q sup equation, and Q sup is equal to Ms over Mf, H4 minus H3 when we're looking at the flow of water, okay? And replacing everything by what it stands for, because we already have all of these, okay? And the only thing we don't have is H4, and we can then solve for H4 and find it to be that 2914.79 kilojoules per kg. And once we have H4, we can then take it and plug it into this equation and read all these other values from the table, and Cp is given to us in the question as 2.6 kilojoules per kg Kelvin, and so we can then therefore solve for T sup. Okay, solving for T sup, this is exactly what you get. T sup will be equal to 257.7 degrees Celsius. Okay, really, really important to know how to do these things. Okay, and so lastly, D, we have to find the percentage of heat lost through the chimney and the percentage of heat lost that has not been accounted for. Okay, the heat lost through the chimney, okay, you can find it using that equation for the heat lost through the chimney, or the heat absorbed by the chimney, okay? And if you look at the diagram for the flow of the flue gas, you will see that you need to find the temperature. Of course, you have the mass of the flue gas multiplied by Cp of the flue gas, and then multiplied by the temperature at the exit of the economizer, okay? Or at the base of the chimney is the same place, TFG5 or TFG4 if you don't have an air heater. TFG5 and TFG4 become one and the same thing if there is no air heater, like in this particular question, okay? And the temperature of the flue gas at the exit of the economizer is the same as the temperature of the flue gas at the base of the chimney, because it goes out of the economizer into the chimney. And that temperature was given to you in the question, temperature at the chimney base as 200 degrees Celsius, okay? And then the temperature out of the chimney, the chimney is releasing the flue gases into the atmosphere. So the temperature out of the chimney is the atmospheric temperature, which is given to you as 24 degrees. I said sometimes they may refer to it also as the boiler room temperature, okay? It's fine, it's 24 degrees. And so you plug in those numbers, okay? Remember again, the mass of the flue gas is 18 plus 1, okay? You plug in those numbers, that gives you the heat that has been absorbed by the chimney, okay, or that has been lost through the chimney, okay. This is what you have here, okay. And now what percentage does that constitute? You will just need to divide this Q of the chimney by the calorific value of the fuel, like we did in that table for the heat balance sheet, okay. Same thing that you do here. You just find the percentage by dividing the Q of the chimney by the CV value, so that will give you the percentage of the chimney, and it's what you get there as 11.33%, okay. And then finally they want the percentage unaccounted for, so you will then do, okay, the percentage that is unaccounted for will be 100% minus the efficiency of the plant, okay, which is 82%, and then minus the percentage of the chimney, which is 11.33%, and what remains will be what has not been accounted for, or maybe the percentage of heat lost to radiation, okay. So 6.67%, that is what you're going to get. All right, so having spoken like that, it has been about an hour, and I hope this has brought so much clarity on steam plants. And again, I cannot overemphasize that what is really important for you to understand is the flow of water and the flow of the flue gas, and understand how you can get the heat absorbed by the different components when you are looking at those two different diagrams, okay. So you have two ways of getting the heat absorbed to the economizer, to the evaporator, or to the superheater. You can get that using the flow of water and enthalpy values, or you can get that using the flow of the flue gas, and then what you will look at is the change in temperature in the flue gas when it gets into a particular component of the steam plant, or a particular part of the steam plants, in and out, okay. The difference between the temperature of the flue gas when it went in and the temperature of the flue gas when it went out. You use that difference and you multiply that by the mass of the flue gas and the specific heat capacity of the flue gas, and that will give you the heat absorbed by the different components, okay. So you have those two different ways of finding the heat absorbed by the different components. So you need to read your question carefully and be able to make sense of that. But I keep saying what is really important for you to know is the flow of water, okay, how it flows, okay. Water flows from the economizer into the evaporator and into the superheater. But the flue gas flows, okay, from the evaporator into the superheater, into the economizer, and then into the air heater, and then into the chimney. So in some of the questions you may not have an air heater, and in others you may have the air heater but you do not have the chimney, okay. So you just need to make sense of all of that. But those two diagrams are really what you need to know and to understand. And so that is it for steam plants, okay. That's me. I was your lecturer for this video. If you wish to have access to more videos, you can contact me on the number in the description below. And also, all the notes that I used in this presentation are also available upon request. This is a video that is available for free, but other videos may not be available for free. So please bear that in mind when you contact me. It takes a lot of work to produce videos of this quality, and so I cannot just make everything available for free. Thank you so much.